you guys have your dyeing homework. I see most people have turned it in. We also, let's see, on Wednesday, you'll have that deal with alder worksheet due. And then on Sunday night, the infamous Sunday night that had you all on a payment over this weekend, that's when the electricity pieces due. I think I clicked the wrong Sunday when the little calendar was there. It said it was due yesterday, right? Everyone was, we didn't even talk about it. Too bad. But no, aromaticity, I think we'll finish it today. But in case we don't, we have to tie up any loose ends. We'll certainly be done with it first thing on Wednesday. And you'll have everything you need to do the homework, study it, and then pop on to D12 and take the aromaticity quiz. So Sunday night, 11:59 p.m. is when that is due. Okay. Now, in terms of aromaticity, let's go ahead and get this so you can actually kind of see it. Can everybody see that okay? Yeah. It's not the brightest thing in the world. It's exactly what's in front of you on your handouts, though, so I think you'll be okay. The idea of aromaticity, when I think aromatic ring, I know the first thing my mind jumps to is benzene, right? Benzene and its different derivatives. But we're going to see that benzene comprises probably the largest class of aromatic compounds, but it is not the only thing that's aromatic. Because it's the largest class and it's common, that's what people think of. But we're going to really expand our definition today and focus on benzene sort of to develop the idea, but then apply that to other compounds that are not benzene. And some of them even have nitrogens in the rings, oxygen, sulfur, things like that. So, we will start out kind of at the beginning with a little history. In 1825, an aromatic compound was discovered. It was isolated from whale oil. And you have to keep in mind, they couldn't do very much in 1825. There were no NMRs, there were no IRs. The idea of bonding theory hadn't been developed. They were just kind of burning things and seeing what their formula was. So they did. Found out it was a carbon for every hydrogen. And then they were able to get a molecular formula C6H6. A couple things they were able to figure out. They tried doing reactions with it. It tended to not do anything. It was really unusually stable. It's a good solvent. And solvents you don't want reactive. So it doesn't do any reactions. It would not undergo addition reactions. So you can't add like HBr to a benzene ring and have it add an H to one carbon and a Br to the other like with an alkene. It doesn't do that. It would undergo substitution reactions. So, in other words, substitution reaction, I could take, there's hydrogen on the benzene, I can take it off and I can put on bromine. That's a substitution reaction. But notice when I do that, I've left the benzene ring part of it alone. And we're going to learn this mechanism in the next chapter. So it would do things like that. But they were things that kept benzene intact. So then the race was on. People were trying to say, what is this thing that we've isolated? And those are the ideas that people came up with. They're kind of interesting. The first one, I sort of see. The second one, a little funky looking, but okay, it looks like a tent. That third one has a bridge in it. And, okay. The fourth one, I do not know what is going on with that. It's bonds going to the center of nothingness. But you have to keep in mind with all of these, they did not have the tools you had. They didn't have the theories you have. The idea of like sp2, sp3 wasn't there. And so they were trying to come up with structures that would seem to work. Yeah?
The last one, are the lines going inward?
They're just going in the center of the ring. It's electrons in the center of the ring.
Okay, so it's not metals more.
Yeah, there's no nothing in there. So, we look at that and we're like, ha, ha, ha. But keep in mind that maybe, this was in the 1850s, 1860s, so 150 years ago. 150 years from now, they may be looking back, saying, they had this idea about sp3 explaining the shape. How stupid is that? So keep in mind that the theory is good now, but they may find that some of the stuff that we hold to be true, like those structures, are not true at all. So, finally, 1865, there was, the story goes, a dream. Casale was part of the whole group trying to figure this out. And he's on a train traveling, I don't know where, in Europe, and falls asleep and has a dream. And his dream was about snakes. And he had slithering snakes in his dream. And they lined up into essentially a circle, all these snakes. One of the snakes fighting the tail of the other snake, fighting the tail, fighting the tail. And it ended up looking this kind of slithering snake thing like benzene. So that was his structure, which we look at and we go, thank God, you know, it's much better than the other ones. All right, so I don't know if you guys have realized this. You will if you ever go into research. That once someone proposes something, it's like sharks in water on this person who proposed it. So everyone went after him, like they do with a lot of new theories, trying to prove it wrong. And what his theory predicted, if you take a look at his structure, is that there were two isomers of benzene. There was the isomer with the double bonds arranged one way. And then I'm going to use my pointer, which I don't even know where it is. There it is. That one. Okay. And then, that's very official, I kind of like that. And then there was the other isomer where the bonds are moved, right? Which was that one right there. Now we know what's going on with that, right? We put a little double-headed arrow in between those, right? And that's resonance structure. But they didn't know that. He said, no, it's two isomers. There are some problems with that idea. When you make 1,2-dibromobenzene, there is only one 1,2-dibromobenzene. And if you look at Casale's model, which is a little tough to see, let's do it over here. His model said, well, there's 1,2-dibromobenzene, right? That's one of them. But since I have these two isomers, I could also have that one. And those are different. You see where they would think those were different? One spans the double bond, one spans single bonds, right? So according to his model, two isomers, you should have two of them, two different types, and there's only one. That was a problem. And what they also discovered, as they were learning about this, is the bond lengths were all equivalent in benzene. And according to his model, it should go short, long, short, long, short, long. Right? They should be different. And they weren't, they were all the same. So then what he said, they of course immediately said, "Hi, you're an idiot, you're wrong. Because we just found all these things that say you're not right." What he said, getting kind of close, is that no, what it actually is it's the two structures, but they're so rapidly interconverting that they kind of blur the one, right? Which is getting there. That's sort of like the explanation for a Chem 400 student who hasn't studied resonance very well. So, sort of getting there. We know that they're not rapidly interconverting, that those are actually resonant structures. The actual molecule has characteristics of both. Right? So, here's some pictures of the resonance representation. We draw just one, because I don't want to sit there and draw both. Right? That's to show resonance. So I just draw one, and you guys are all supposed to understand, okay, that it's actually the pi bonds are actually delocalized over the whole molecule. So sometimes you'll see that. You guys have all seen that picture? That's what that's implying. It's implying that no, there's no double bond here, and there's no double bond there. It's the pi electrons are over the whole molecule, and the actual bond order, well, it's not double, and it's not single, it's halfway in between. It's a bond and a half all the way around. I'm not going to usually draw it like this unless I want to show a benzene and I'm focused on something else. Because if I'm showing you benzene, like I will be for the next week or two, I'm doing reactions with it, and I need those pi bonds. So I'll draw something like this or something like this, and you need to understand that it's actually a bond and a half. The electrons are delocalized. Showing some bond angles here and bond lengths just for your interest. The picture that you can draw, this picture is a little funky, kind of ignore that one. This picture here, every carbon has a p orbital, and the electrons, there are 6 pi electrons. They are delocalized all throughout the pi system. And it's showing like a donut on the top and a donut on the bottom, because remember the electron densities in both lobes of the p orbital. You know, we drew a pi bond, and hopefully no one had any trouble with that, right? That's what that picture is showing. It's just all the way around. All right, so we have some ideas about what benzene now looks like. Let's take a look at its stability. Remember, they found out when they originally isolated it that it was unusually stable and inert. We're going to find that to do reactions with benzene that actually disturb the benzene ring, it is hard to do. You have to have powerful catalysts. You have to have oftentimes temperature and pressure. So those aren't benchtop kind of reactions in general. We're going to have to do special things, a lot of catalysts to make it go. So there is some kind of extra stability going on. What is that? Well, it's covering up a key part of our whole talk. There you go. All right. Okie dokie. Now we're back. So, what we have here is one of those energy diagrams, and what we're doing is we are taking and doing a hydrogenation. And so you can see here we have one double bond, and we're adding H2, and everything's going down to cyclohexane in this. So that slide is a heats of hydrogenation slide. So you can kind of build up. If you have a double bond, your baseline is 120 kilojoules released. So, and I'll sort of, you guys can draw on your slide. I'm going to augment it with some stuff here. So the base, when you're doing 1, and we have H2 going to that, delta H is negative 120 kilojoules. So when you have 2 double bonds, which is the next one over, it is that one right there. When you have 2, it should be double that, 240. Now what's special about the 2 that I drew right there? Or that someone drew. I didn't do this, but they're isolated, right? Okay? Why is that important? If they're conjugated, what happens? It's a little more stable, right? We saw that last time. So right here, this is isolated. So make a note of that. This guy's isolated. Right next door, this bluish color, conjugated. And if you take a look, that caused a drop of about 8 kilojoules. I think when I gave it to you guys, a week ago, we were working in K-House. So your numbers will be a little different. Hang on one second, pick it up. So notice it's a little more stable. That is resonance energy. So that's the energy that comes from that extra delocalization of electrons that the isolated case doesn't have. Yeah?
Just so I make sure, if you had cyclohexane and you wanted a double bond, you have to put that much into it?
Right, exactly, yeah. All right, so now we're going to put 3 double bonds in. 3 double bonds, you would predict, and we know this is wrong, but here's 3 of them, so times 3, you would predict a delta H of negative, this is higher math, let's go, negative 360, right? They have a 359, so there must be some rounding going on. Here is the predicted, right there, that level, right there. We know that, at the very least, we have some resonance, okay? That resonance should drop it a little bit. So I can say, up a little bit so you guys can see, but this will be lower due to resonance. And we saw that when we had the diene. So if I can do a resonance structure for that diene, I can move things around, it would save 8 kilojoules. So here, I can do a resonance structure here, and I can do one here. So that would involve all 3. So maybe 16 lower, something like that. Should be somewhat lower. Take a look at what happens. So let's say the best case, one resonance structure lowers at 8. I can draw how many for that? 3? I think. These are three reasonable resonance structures. 8 times 3 is 24. So you'd say, okay, it should be more stable, about 24. Check it out. 151 kilojoules of resonance energy. It's huge. So you figure you would think lower by 24 kilojoules, but it is lower by 151 kilojoules. So there is clearly something else going on. There's no way you can draw enough resonance structures that it drops it that much. That drop of 151 is huge. And that's what makes benzene special. It's much different than the 1,3-butadiene thing that we, or 1,3-cyclohexadiene that we had on earlier. Okay, so now we have some explaining to do. We are going to spend a lot of time explaining that gap right there, the 151 kilojoules. And as we go through and do that, we're going to explain a few other things too. So here's some things. We got the huge drop in energy, can't be explained by resonance alone. Okay, there we go. Okay, you can have, this is going to throw a wrinkle into it. You can have cyclic compounds that are similar to benzene. They look like they should behave exactly the same. So, looking at this has resonance. And looking at the example up there, that has resonance. This is very stable, weirdly stable. This right here, we are going to see is very unstable. Like in a not able to isolate it kind of instability. Okay, hugely unstable. So the resonance argument completely isn't working. It doesn't explain the gap, and it completely blows up. So there's something else going on. The key is in this bottom statement. It has to do with looking at the pi-MO diagram. You guys have heard a lot in 305, 400 about the closed shells, right? The idea of the octet, you closed all those bonding orbitals, right? Made it really, really stable. You never wanted to violate the octet. Well, benzene has a really similar thing. We're going to do a pi molecular orbital diagram. We'll have bonding orbitals, anti-bonding orbitals. We'll see that things that are really, really, really stable have all the bonding orbitals filled. That way, if I take anything out, I've disturbed it. If I add anything in, it's going into an anti-bonding, which is not stable. So we need to build a pi-MO diagram for benzene. And this is, it's actually kind of fun. So, let's see if we have anything about it. Nope. It's the summary, so we're going to kill that for a few minutes, and here we go. It's going to be really interesting to fit it on this, so we'll do our best that we can. Back. I may take advantage of this thing here. I think it'd be easier. Okay, I want one big contiguous chalkboard. Can everybody see that okay? Yes? Okay. Here we go. Now, if you remember when building MOs, you guys had these criteria. I think we talked about that. That the number of molecular orbitals was equal to the number of atomic orbitals used, right? So we did 1,3-butadiene, we put in 4 p orbitals, and we got out 4 molecular orbitals, pi molecular orbitals. So that would still hold true. The next thing, the MOs are going to be divided evenly between B/T's between bonding and anti-bonding. We may have some non-bonding in there, and I'll show you how to determine if you do or not as we go through. And lastly, the MOs will be symmetrically distributed above and below a non-bonding line. So, for benzene, we have 6 p orbitals. And what we're going to do is, we go to the center here, and we're going to, just feels weird. We're going to draw benzene, flat, kind of flattish like that. And then you're going to wish you had a stamp for this discussion, go like this. We're going to be drawing a lot of these. Okay, so what we are going to, this is our line, sort of our zero energy line. Right there. And that's the line that the orbitals have if we don't know, sort of our non-bonding line. So the best we could possibly do is where there are, remember, nodes increase as we go up, right? So the lowest energy thing we could do is something with no nodes. And if I draw it down here, you guys can't see that, can you? Better? People see it now?
Much better.
Much better, okay. So we're going to draw the one with no nodes. So go way down low on your paper, and can you see this?
Yes.
Good. If you can't, you can probably imagine it. I'm going to shade them because I'm too lazy to do pluses and minuses. I'm shading all the tops, all the way around. And this is no nodes. That's my lowest energy bonding MO. So there it is. Then as we go up, we're going to have one node. And we're going to draw it such that the node is symmetric. So I don't want to draw some node where I cut off just one carbon. So I am going to put a node straight down the middle, right down here. Okay? And like this. Here's my node. Draw my p orbitals. Everything on this side of the node is shaded the same way, so I'll shade the top. Then I come across the node and I flip my shading. It's an anti-bonding interaction, so we'll shade the bottom. And then everything on that side of the node is shaded the same, so they're all shaded on the bottom. Now I put that below the line, which implies it is a net bonding orbital. So we're going to do a little bookkeeping right now and see if that's true. In terms of my bonding interactions, I have a bonding interaction there. I have a bonding interaction here. I have one, that's a bad drawing. I have one here, and essentially one there. Right, that's where there's no canceling occurring as they overlap. Here is an anti-bonding and an antibond. So the net, 4 bondings, 2 antibondings, it's a net bonding orbital. Does everyone see that? Okay. Now I could draw my node the other way too. Instead of going straight down, I go straight across and cut the ring in half that way. And so I'm going to draw that. It's a little weird when they draw the node where it passes through a carbon atom, just like I've done. A node is essentially nothing, right? It's 0 electron density. They don't draw the orbital. We just kind of ignore it. So, doing that, above that node, favorable interaction. And then below the node is also favorable. And I'm going to just draw them shaded on the top. It doesn't matter because I never have this orbital interacting with that one in a positive or negative way. They're spaced by this node right here. Right? So they're never, this carbon is too far away to interact with that. So I don't have to worry about flipping the sign. So this guy had net 2 bonding. How many net bondings there? 2? Everyone see that?
2.
This is net 2 bonding too. So let's go up here with that. So they both have the same number of bonding interactions. So those orbitals, those two MOs that I drew, energy-wise are the same. They're degenerate orbitals. So what I'm going to do is go like this. My bonding, my bonding. All right. Let the fun begin now. 3 nodes. No, 2 nodes. Where did 3 get? Okay. So I'm going to pop it up here because I know the answer, but you would have to work this out. So 2 nodes. Let's go. What is the best way? I'm going to use my cheat sheet here. I don't want to intersect any atoms with one of them, so it's got to be symmetric. Okay. Okay. So every carbon that doesn't have a node gets a p orbital. So we all do. And here we go. You start at the top, and I'll shade the top. The one next door to it, going clockwise, there's no node in between them, so we also shade the top. Then a node, so I have to flip my shading. Bottom. Then a node, so I flip my shading back to the top. Then I stay at the top. Then a node, so I can flip again. And then I always sweated this out as a student. You're committed now, so you have a node here, it had better have flipped. And it did, so you're good. Okay, everyone okay in how I did shading? All right, now let's count up interactions. We have a bonding, an anti-bonding, an anti-bonding. A bonding, an anti-bonding, and an anti-bonding. What happened? 4A and 2B, so it's net 2 antibonding. This is an antibonding hot molecular orbital. Okay. Now, let's go ahead and you can draw another one. Put it right here. And now I'm going to have to go through atoms. So let's go like this. We've got to cut it evenly. Let's go like that. Right. We'll start putting our orbitals in. We don't have to put orbitals where the node actually cut through the atom. So we have there, 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 there. All right. So start at the top left-hand side and shade the top. Going clockwise again, I go across a node, so I shade the top. Then there's a nothingness, so now I don't have to worry. Right? I just hit a node, big deal. So this next one, I'm just going to shade the top. You could shade the bottom, it would not be wrong. Okay, you're kind of given a free pass on this because there's nothing in between this guy and that carbon. There's no node there. There is a node in between these 2 adjacent ones though, so I have to flip the sign. And then I'm done. So next, what do we have? Antibonding? Antibonding. This interaction that is right here is essentially a non-bonding interaction. It doesn't count for anything. So I have a net 2 antibonding. So these 2 depictions are exactly the same energy. So I can come over here. That's pi star. And that's pi star. I always loved the highest level one because what happens? It's always opposite, every single one, right? So going to the highest level one, I have a node there, I have a node there, I have a node there. And I'm just going to alternate like crazy all over the place. So I'm going to go up, down, up, down, up, down. There's nothing good about this at all. And so that is my worst one. Yes?
In the same way, how we drew degenerate orbitals for the previous 2, couldn't the last one also be shifting and also?
You could probably, yeah, I think you could do the other, could you do the, you could go through I think you could, you can come out okay.
Is it?
But, well, typically, the very highest one, you show all the orbitals, and it has as many nodes and as many flips as you can do.
Oh.
They try to maximize that. But I think if you had shifted it, you still would come out okay.
Yeah.
I think you still would be the same, yeah. All right, let's go ahead and put electrons in. Benzene has 6 pi electrons, so let's pop them in there. There's 1, there's 2, 3, 4, you don't pair unless you have to, 5, 6. That's benzene. So, what do you notice about that?
They're all in the,
They're all in the bonding, yeah, so benzene has a filled pi MO diagram. Let's say bonding. All its bonding orbitals are filled. It is, in effect, closed shell. It's closed shell. So anything I do to those electrons in that ring, whether say I do an addition reaction and I take 2 away out of the system, I've wrecked the closed shell. If I put any electrons into it and make it negative, then I have to put those in the anti-bonding. It's not a closed shell anymore. So benzene is very resistant to doing anything because it's noble gas-like, essentially. All righty. Now, we understand the stability of benzene. Let's work on the instability of the 4-membered ring. And then I'm going to show you guys a shortcut. This is all very interesting. It takes a lot of time. So we're going to do one that is 8 carbons? Yeah, 8 carbons after we do 4. You're going to be really good at this one. So let's take a look at this guy. So we draw our p orbitals. I can have my best case scenario. They all overlap in a bonding fashion. So that's going to look like this. And that would be a bonding number. Going up a level, I'm going to show you my drawings, is 1 node. So, go like that. There's 1 node. And bottom split there, across the back. That's one way of doing it. Let's see what ended up with our interactions. Here I had bonding, 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 4 bonding, so it's good. Here, I have an antibonding, a bonding, and there's a bonding, an antibonding. What's happened?
that's 0.
0, what is that orbital? It's a non-bonding orbital. It's neither bonding nor anti-bonding, right? It's a non-bonding. So I'm gonna move myself over here for a minute. So I have at this level a non-bonding orbital. Now I can put a note another way. Let's put it. One book that I was looking at put it across this way, like that. But I think it'll work the same. It's a little more interesting to put it like that. I think this works too. So we're going to top, and then we don't worry about it. And then we can just top there, we don't worry about it. Any anti-bonding interactions? No. Any bonding interactions? No. So it's another non-bonding orbital. Kind of cool. And then the worst. Would be 2 nodes, and I'm sure you guys can guess, it's going to alternate all around. And that is completely anti-bonding. Now remember what we talked about with this guy. This was completely unstable. Like, it can't be isolated, unstable. So, let's see what happened to it. Even though it has resonance, it's totally unstable. So I have 4 pi electrons. Here's 1, there's 2. There's 3, there's 4. What do you see? Okay, electrons in a non-bonding orbital, which we've had that before, right? That's not fatal in and of itself. There's something worse, super bad.
They're not paired.
They're not paired. What's an unpaired electron called? Radical, right? And we ran into those with free radical halogenation. Remember we talked about how if your halogen was really reactive, like F dot, you can get explosions. This is super reactive. Cl dot is fairly reactive, bromine a little bit less so, right? This is a diradical. Imagine how bad that is. So looking at this, what we have is a diradical. That is going to be really unstable. So resonance would tell us, if we didn't know it was unstable, I'd look at the structure and say, I can draw a resonance structure, this should be pretty good. The MO diagram tells us the truth, and that is that it is really going to be unstable because it essentially has radical character times 2. Bad. Okay, now that you're feeling comfortable, let's go ahead. We need a really big board.
You don't have this.
We can make this work. Super big board. We're gonna do this guy. And this will be fun. So let's put it up here. And draw it just like I am. Start like that. And follow me along, otherwise it's gonna look bad. Go like that. Then come straight down on both sides. Then come over. Probably gonna look bad anyway, following me. There's that. And then come across. Okay. Then put in pi electrons. So we have 8 carbons, 8 p orbitals. We should have 8 pi molecular orbitals. On the test, I may give you 10. Which is terrible, right? It's going to be this, like, huge. Okay, I'm going to show you a trick. We're not actually going to do this one. We are, but we're not going to do it like that. I may ask you, on the test, I could give you something like this, and say, show me the MO diagram. I will not ask you for something this big to recreate the whole thing, because it takes too long. I don't want to spend 20 minutes on a question. I may ask you, though, draw me the, I don't know, second lowest in energy molecular orbital. So what I'd be looking for there is you'd say, okay, here's the lowest, it has no nodes. So if I say draw the lowest, I'm not going to do that, but if I did, draw the lowest, it has no nodes, you just draw it. Draw the next lowest. Well, you know in your head, okay, going up one more, it has 1 node. So just draw me something with 1 node. You can draw either this or that. No, I probably wouldn't ask for both. I just say draw 1. And I may say draw the lowest energy anti-bonding orbital. Well, you think to yourself, okay, that would have to have 2 nodes, and just draw one of these. Okay, that's easy. Recreating the entire thing is what takes it darn long. So we're going to learn something called the polygon rule. And the polygon rule says to arrange the polygon or draw it so that a corner is at the bottom. So not like I just did here. I had the flat part at the bottom. I have to draw it so the corner is at the bottom. Then draw a line from each carbon. That is your pi MO diagram. So let's do it with benzene first, and then I'll show you my shortcut to this because I can't follow those instructions. So, and you'll see why in just a minute. So benzene, if I say draw the pi MO diagram, not the orbitals, I think just the diagram. Okay? There's benzene, corner to bottom, right? So I've got it set up correctly. Then you go like that, like that, like that, like that, like that. Lo and behold, look at that. There. And you know the non-bonding is in the center of all those, right? Because they're arranged symmetrically above and below. Okay? That square that we did, right? I drew that one wrong. It should be pointed at the bottom, and now here's why I don't do this. I can't even do this. It should,
Just go right.
like that?
Yeah.
Yeah. Okay, it should look like that.
That's sort of correct.
Sort of like that. One. Yeah. Isn't that cool? In the center is the non-bonding line. Pretty neat. Now the 8-membered ring are bigger. I can't draw them with a point at the bottom. I cannot, like if I were given this on a test and I went to redraw it, I would mangle it and then problem wrong. So what I do, I don't do this. I just go, okay, that is my bottom, okay? And then I stand back, and I go like this, and I straighten it out. So that, it's cheating. That, and that. And I know that this, that's my non-bonding ring. Pretty handy, huh? Okay. Now, in terms of things being aromatic, for something to be aromatic, which means unusually stable, it has to have a filled pi MO diagram. And there are actually 4 criteria that you have to satisfy as you're going along with this. So let's list them up over here. Okay. Grab it, make sure I'm forgetting. And some of these are criteria that allow you to build a pi MO. So you have to be able to have all the p orbitals interact in order to even talk about this. So here are the 4 criteria for aromaticity. Number 1 is a compound has to be stable, and you have to have conjugated pi bonds. So what this means is we are not even going to have this discussion with that. That cannot be aromatic. Okay, so you really cannot have any sp3 carbons in there, sp3 atoms. That ties into number 2. As a result of this, it must happen that each atom must be sp2. You have to have a p orbital on it. That's the real big thing. And we're going to see this pop up in just a little bit when we test other compounds that have like nitrogens and sulfurs and things in the molecule. We are going to say, well, to even have this discussion, I'm going to force that nitrogen to be sp2. Because if I allow it to be sp3, there's no point going any further, because I'm done. Right? So we will force atoms to be sp2 and see what happens. Okay, 3rd thing. I have to be able to have all those p orbitals line up at the correct angle. There has to be overlap in between them, which means I can't have an atom going and twisting and not being planar, right? So in order to be aromatic, you must have a planar structure. Because if you don't, then the p orbitals cannot overlap. If they can't overlap, you don't have pi MOs. And number 4, this allows you to draw your MO diagram. Number 4 is the big thing, is you must have a closed shell configuration in your MO. Now we're going to learn another little shortcut. So we learned a shortcut how to draw. It turns out, and you guys can prove this to yourself, that this number 4, this happens when you have 4n plus 2 pi electrons. There's some magic numbers that consistently will fill the shells. As your MO diagrams get bigger and bigger, there are only going to be set numbers of pi electrons that will satisfy this criteria. And it ends up that it's 4n plus 2. It's called Hugel's rule. It's 4n plus 2 pi electrons. N is nothing magical. N is just a number. So N could be 0, 1, 2, 3, etc. It has nothing to do with the numbers of carbons in the ring. What this is saying is I can have a closed shell configuration if N is 0, potentially with 2 pi electrons. And you could just memorize the numbers if you wanted to, but it's 4n plus 2 is easier. If N was 1, then with 6 pi electrons, that's okay. If N was 2, 10. If N was 3, 14, etc. So if I gave you something that had 12 pi electrons, you know it's going to violate Hugel's rule. It can't be aromatic. Right? So just memorize 4n plus 2. It's very helpful. Okay, so here is some more rules. My eraser. Can't fit in there, so let's fit in here. If 1 through 4 are true, the compound is aromatic. And it will be unusually stable inert, blah, blah, blah. If 1 through 3 are true, but you have 4n pi electrons, so you don't have that extra set that you need, that extra 1 pair of electrons, you only have 4n, then that is going to be a compound that has an unfilled shell. It's going to be very reactive. And they have a word for that. They call those anti-aromatic. It's like the opposite of aromatic. So we have anti-aromatic and aromatic. Aromatic is 4n plus 2, and everything else is okay. Anti-aromatic, 1 through 3 are okay. It's looking like it could be aromatic. You go and count those electrons, they're wrong. This is going to be 4n pi electrons. Okay? Then we have our third case. If 1 through 3 fail, any of them fail, we're not even discussing aromatic or anti-aromatic. This is just a plain, boring, non-aromatic compound. So we'll say non-aromatic or normal compound. Okay? I think it helps in the discussion we're going to do to put a little energy diagram up. Not a big one, don't panic. Just go like this. Normal compounds have nothing special about them. They would be like a 1,3-cyclohexadiene. They're boring. Nothing special. So their energy would be right here. This would be non-aromatic. There's nothing real stable about it. There's nothing real unstable about it. They're just there. Aromatic, they're much more stable. And they're much lower in energy. So we'll see things that are non-aromatic, but maybe if the hybridization were different and they could gain some electrons, could become aromatic. And we'll see cases where you have anions that are aromatic. You gain some electrons and it's much more stable. Anti-aromatic is up here. We're going to see some compounds that are anti-aromatic. And they're very, very unstable because they have 4 pi electrons. But it's a bad thing to be way up here. It'd be far better, instead of being anti, just to be non-aromatic. It's lower in energy. So what these compounds will do, if they can, when they're completely flat, they're anti-aromatic because they satisfy rule number 3 as well as the others, right? But what if that compound took one of its carbons and went zip with it? All of a sudden it flunked and it's non-aromatic. So a lot of the things that would be anti-aromatic on a piece of paper, they look like they should be, they actually are somewhat bent, and that brings them down here. Okay? So we're going to go through and look at a couple of examples. All right, this just sums up what we just talked about. We have some examples. Tell me about that guy. Is it aromatic, non-aromatic, or anti-aromatic? Non. Why do you say that? It's it's got that right there. You see that? That's an sp3 carbon in the ring. That ruins our discussion. So that sp3 carbon, oh, that's hard to see, is non-aromatic. Yes?
Could you also argue that it's non-aromatic?
Oh, absolutely, because that's a tetrahedrocarbon. Okay, next one. Do you have fully conjugated pi bonds? Yeah. Okay. Each atom is sp2 hybridized. Is that true?
Yes.
Structure must be planar. I don't see a good way that thing could twist out of planarity. All right, hard to say, but let's assume it's planar. Okay, so 1 through 3 is good. Okay, how many pi electrons?
8.
8, which is
Not the number.
4n, right? So, because 1 through 3 is okay, we have 4n pi electrons. It's really hard to see. That says anti. It's anti-aromatic. This is hard on homework and things to tell. The big thing that's difficult is planar. Is it planar or not? And I will give you guys clues. Like I'll have 2 hydrogens that are both wedges sticking straight up. And the only way they can do that is if the molecule is shaped like that. Okay, so I'll try to give you clues. Okay. Like that. All right, take a look at that. It is, look through cyclic and conjugated pi bonds. Are there any sp3 atoms popped in there? Okay, so number 1's good. Each atom's sp2 in this substrate. Structure must be planar. Okay, let's put, I don't know, let's kind of ignore that for a minute. Count the electrons. 10. Okay. So it has 10 pi electrons. So does that fit 4n plus 2?
Yes.
Yeah, it does fit 4n plus 2. But take a look at that. Turns out, tough to see, that a molecule like this, to be planar, the hydrogens end up pointed to the center of the ring. And there isn't enough room for that to happen. And so what this guy does is it actually is forced to twist. And since it's forced to twist, it doesn't become anti-aromatic, right? Not that bad, but it does become non-aromatic. So the hardest part really is the planarity issue. It really is. Okay. What do you think about that one?
Looks familiar.
Looks familiar. That's what you're using in lab today. Okay, well, is it cyclic with conjugated pi bonds?
Yes.
Every atom is sp2?
Yes.
Yep. Planar?
Yes.
Assume so, yeah. How many pi electrons?
14.
14. Does that fit 4n plus 2?
Yep.
Yep. So, it says aromatic up there.
Yes. Oh, it does.
I'll get rid of red in all my other slides. This isn't working so well. It does say aromatic. You know, if I can figure out how to work the lights, I'll probably sink us into darkness irretrievably by doing this. Let's see. No. Did that help at all?
Yeah.
Okay, all right. All right, now this next one. Whoa. Okay. First check, the first thing I always do is I try to find an sp3 atom, because then I don't have to go any further. There is none, that's bad. So every carbon's sp2. We can assume planar. Okay. I don't see how that would twist anything else. Count those electrons, my word. 2, 4,
It's 20.
14, 16, 18, 20 pi electrons, right? Okay. So tell me about that.
That's
What rules
4n.
that fit? It's 4n, that's a bummer. And so what that is telling you is anti-aromatic, right? Okay, so are you ready for the answer?
Is that right?
1, 2, 3 is okay? We agreed on that? Failed 4n plus 2? So far so good?
Yeah, see.
It's aromatic.
Totally that.
That's totally bad, huh? Turns out that these rules that we're going through fall apart when you're looking at polycyclic molecules, which are, multiple rings attached to each other like this. And so what we are going to do is do a little modified Cooper rule. And then we'll try it on this and see if we can come up with the right answer. So, I need my lights back. So for polycyclics, you gotta do a modified Cooper rule. What you want to do is you want to draw your molecule with the maximum number of double bonds to the exterior. In other words, when I say that, what I'm talking about is here's the exterior of the molecule, the outside borders. That's interior, that's interior, that's interior. Okay? So try to draw as many as you can on the exterior. And then what you're going to do is don't count the interior double bonds. Don't count those interior pi electrons. And this fixes it. So what we do, take a look at our structure up there. This says, okay, for the modified rules, polycyclic, we're going to ignore this one right here. And we're going to ignore this one right here. And that one right there. Okay. So when we do that,
14.
it drops this guy down to 14. And that fits 4n plus 2. And the answer comes out right. And you only have to do that when you get into molecules that look. Okay? Questions so far? Yeah.
So that only applies when do we still go through 1 through 3? 1 through.
You still have to go 1 through 3,
Okay.
right? But when you're counting your pi electrons to see if they fit 4n plus 2 or 4n, you ignore the ones that are in the interior. So 1 through 3 still has to be gone. All right, now we're going to kind of stray from this and look at rings that are larger and then rings that don't have just carbons in them. And really the ideas we've talked about are the same, so it's a bunch more example problems really. So, here's our All right, here's large ring annulenes, and annulenes are ring. The thing that gets interesting about them, when they're large and when they're not all fused, like those really big polycyclic ones we were looking at, is they get some flexibility in them. So what they can do is they can be planar, that's fine. If planar is bad, so let's say being planar puts them up here, anti-aromatic. That's a bad thing. So they can also, when they're big enough, we're looking at like 8 carbons and above here. That's big. They can tweak a carbon out of plane and then drop down to non, which is better. Okay? So an example of that is this guy right here. If you take a look at it, and we assume it's planar, it has 8 pi electrons, it fits 4n, you would predict anti-aromatic. Because if criteria 1 through 3 fit, and it's 4n electrons, it's anti-aromatic. It turns out, though, that cyclooctatetraene is not particularly unstable. It's not particularly stable. It's not particularly unstable, it just kind of exists. So what happens is that it is flexible enough that it tweaks itself. That's more of a picture of what it looks like. The ends kind of fold up. So the minute that occurs, then you fail the third rule, which says has to be planar. What that really means is the p orbitals don't line up anymore. So you don't have an issue with all those pi MOs, that system doesn't exist anymore. And so then it becomes just plain non-aromatic. So 8 carbons and above, you'll see that. You'll see things that you look at and you say that should be anti, and they'll tweak something, and they're not. They'll be non-aromatic. All right, let's take a look at an extreme case. Woo-hoo. This is huge. Let's see what it is. It could tweak. Okay, this would easily be able to go if it had to. Let's see if it has to. So, go on the hunt for the sp3 carbon. Not there. Okay. So, fully conjugated, alternating pi bonds. Assume planar for starts. Doesn't have to be, but assume that it is. How many pi electrons do we have? How many? 18. Okay. 18 pi electrons. And does that fit 4n plus 2?
Yes.
It does. And so is this going to be planar?
If you have something again about it.
Yeah, it has a lot to gain by being planar. By being planar, this thing can be aromatic. It can be extremely stable. There is no reason at all for it to not be planar. And so it will be. This is a planar molecule, and it is aromatic. If it were to tweak itself somehow, it loses that advantage. And that's not going to happen. Okay, so this discussion really boils down to, the 4 plus 2, 4n, what's going on with your pi molecular orbital. Remember, the goal is to get that pi MO bonding set filled, so we have a closed shell. So what we're going to see is ions that can be aromatic, something that, when it's not an ion, is not aromatic. But if it either gains or loses electrons, it can become aromatic. So here's an example of cyclopentadiene, which we saw a lot in that Deals Alder worksheet that you guys are doing. Cyclopentadiene is kind of strangely acidic. You can take a base that is not, a huge, like the flaming base, one of the butyllithiums. You can choose a reasonably weak OChem base. Deprotonate the hydrogen and put a negative charge in the molecule. And that happens pretty easily. Normally, to deprotonate an sp3 carbon has a pKa of like 60. It is not an easy thing to do. It's really hard. This is pretty easy. So what that tells you, if something deprotonates pretty easily, it's telling you the conjugate base right here is stable, right? So our question is to figure out why that thing right there is stable. And it ties into, guess what? Aromaticity. So what we're going to do is we are going to force that carbon with the electron pair to be sp2. And this is where the next couple of molecules, we are going to say, okay, you are sp2. We learned carbanions are normally what? sp3. We're going to force this to be sp2 because there might be some advantages to that. Okay, so force it to be sp2. That means there's a free p orbital on every atom. Okay, that's good. I'm going to assume it's planar. If I count up the electrons in my p orbitals, the two double bonds are easy. That's 2, 4. I just force that lone pair to go into a p orbital, not into an sp2. So that's 2, 4, 6. That gives it 6 pi electrons in the pi system. And what that means is closed shell. It meets 4n plus 2. The anion is aromatic. And that's why it's so easy to make it. It's really, really stable. And I couldn't have had this discussion if I had not forced that carbon to be sp2. Okay, tell me about the corresponding cation. Yeah, that's, the cation is really, 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 really hard to form. Really hard. So, it's going to be sp2 carbon. And it has 4n pi electrons. It's anti-aromatic. It's not very stable at all. How about that one? Carbon sp2. If I do that, here's an issue where we talked about how you have to have conjugated pi electrons, right? And there's no lone pair for the pluses, right? So that causes some people some trouble. Can I conjugate through there? You can. Because you guys could draw a resonance structure where I could flip these electrons over, bring these over, flip that down into the plus, right? And it would then put the plus right there. So I can move that plus charge around the ring by moving the electrons. So that carbon with plus charge is in conjugation with those pi electrons. Now I just move the plus around. So with that said, if we make that carbon sp2, which we have to do to see if this will work, assume it's planar. How many pi electrons do I have? 6. And what would you say it is? That guy's aromatic. Okay, now for a fun one. A dianion. Yeah.
For molecular orbitals, if you fill all the bonding orbitals and you fully fill the non-bonding orbitals, can you count that as aromatic, or is it just the bonding orbitals that have to be filled?
This is an example of that. If you draw the MO diagram, we're throwing electrons into the non-bonding, and it's going to come out that this guy's aromatic. Yeah, it's aromatic.
So non-bonding orbitals can.
Non-bonding orbitals. Okay, so looking at this. This is that 8-membered ring that we just took a look at, and the ends folded up so that it wouldn't be anti, right? Let's take a look at it now. I threw some electrons in there. It's got a 2- charge. Make every carbon sp2. Force it to be. If that's the case, I can draw a lot of different resonance structures where I move the lone pairs around. So, 1 through 3 is okay. We'll assume flat and see if it works out. All right, how many pi electrons if I make all those assumptions? We can count the lone pairs now, right? Because we're throwing them into p orbitals. So 2, 4, 6, 8, 10 pi electrons. Does that fit 4n plus 2?
Yes.
It does. So it turns out that this is aromatic. And what happens if you have those extra electrons gone, this thing would be anti-aromatic. It will fold up. You make it an anion or dianion, and all of a sudden it's very good to be flat, and it will change its geometry. And the dianion is actually flat and really stable. Okay. Okay so far? All right, we're going to move now to, quickly, we'll do one example and we'll finish up next time. Heterocycles. This is where we have rings, and we can talk about the same kind of rules we talked about, so they're pi bonds. But we have atoms in the ring that are not carbon. So you'll see these atoms are typically going to have lone pairs associated with them. So nitrogen, oxygen, sulfur, phosphorus, those sorts of things. So this is an example, it's pyridine, which is that base that we kind of threw in on everything last semester. It's a non-nucleophilic base. And with pyridine, I have a nitrogen in place of a carbon. And the challenge for these molecules, they're a little harder initially, is you have to force the nitrogen to be sp2 to have this discussion. Because otherwise the thing can't be cleaner. So I'm going to force it to be sp2. Then the challenge becomes you have to figure out in what orbital is that lone pair. Because I need to know, do I count it as a p orbital set of electrons, or do I not? Okay, so I've got to figure out what orbital it's sitting in. And so, if I make that nitrogen sp2, now let's just draw it here. Then I have 3 sp2 orbitals, right? And I have 1 p orbital. That's the identity of the nitrogen. The p orbital, if you look at that molecule, it's used to form the pi bond. Does everyone see that? I have used it. So the lone pair cannot be in the p orbital, because the p orbital is busy making the pi bond. So what that means is that my lone pair is in the sp2 orbital. Can't be the p's. Everyone okay with that? Because that's the key thing with the heterocycles, is identifying where the lone pair is. Okay? So if it's in an sp2, do I or do I not count it as my p orbital count? I don't. It's not even in the system. The p orbitals, here's a picture of it. See how they're sticking up and down? That's the p orbital electrons that I care about. The sp2 orbital, it's sitting right there. The lone pair is sitting out here, completely away from all this. So I'm not going to count that lone pair. And so what that means is that, let's flip back to it real fast. I'm not going to even count it. So I have a ring. I have 2, 4, 6 pi electrons in the ring. Pyridine is aromatic. If I counted the lone pair, I would have said it was anti. I would have been completely wrong. So your exercise is to go home, and you have a couple other examples. See if you can figure out where the lone pairs are. We'll finish this up first thing next time, and then we'll name